Hello.
Hello.
I hope you had a good break.
I did. How
Wonderful.
about you?
Oh, it was great. It was a good break from everything.
Yeah.
So
I'm hoping I
really-
didn't forget everything.
exactly. So let's get back to it. So we are approaching the end of the term, pretty much, and most of the topics that were needed to be covered have been covered. There's only one topic that I want to discuss more, and that's the operational amplifiers. The I mean, if you look at the theory of that, it seems quite complex when you observe it, but when you really get to the detail of it, I mean, it's very straightforward application, where there are specific type of operations, like if you were to amplify a signal, you'll use the operational amplifier there. So a weak level signal needs to be boosted up to a certain level. Of course, it doesn't uh, happen. So we basically follow the rules of physics or law of conservation of energy holds. So essentially, we apply additional voltage to the op amp circuit, which allows to boost the signal. But again, the goal is to boost up the signal to the desired level. So for that purpose, we use these. And if you recall from our previous course in digital electronics, um, I talked about using the transistors for the purpose of digital application. And transistors have three modes of operation, right? So there is a mode of operation where it acts as a open circuit. There's a mode of operation where it acts as a short circuit, and there's a which I mean, those two modes are ideal for for digital electronics, because you want zeros and ones. So a short circuit and open circuit serve that purpose. Whereas in case of analog circuits, we want to amplify signals to a desired level. And the third mode of operation of transistor, which is the variable resistance mode. So depending on how before it reaches saturation, and so between saturation and cutoff, there's a certain area where it acts as a nonlinear circuit essentially. So you can be used as a variable resistor. So that is useful in this case. And in terms of the actual internal structure of these op-amp circuits, I mean, that's not really of interest to us in this course. But of course, when you take the next course in electronics, you will look at these circuits and designing the various kind of amplifiers in detail, and what it takes. So basically, you would create a resistive network around a transistor to create a certain type of amplifier, and that will be the focus of the next course. For us, we just look at it as a like a black box kind of circuit, where you provide a certain input and you expect a certain output depending on the various components that you provide around it. So with that context, let's talk about it. So again, as I mentioned, the theory is quite complex, but I guess application is pretty straightforward. There's certain formulas that you would have to consider, and you bring the circuit to a simplified form, and after that you can apply that formula and be done with this. So in today's lecture and the next lecture, I will go over these details in terms of the application, and what entails regarding these type of circuits. So here, the I'll just provide some basic definitions. So if we represent this source voltage using its Thevenin equivalent, and here we have a certain load tied to it. So the amplifier sits in the middle. Okay, so this is our source, this is our load, and this is our amplifier. So these are the three stages. And essentially, if whether this is the source resistance, so we can, in other words, we can say this is our input, this is our output, and this is our gain, right? So in other words, our output should be equal to gain times the input. So by the amount of this gain, we're amplifying this signal, the input signal. So that's the boost that we're giving to it, right? If we were to assign voltages, for example, if we have a voltage here, this is VL, and typically the symbol for gain is A, right? Then we can say that the output voltage is represented by V sub L, the gain is represented by A, and the source voltage is V sub S. Okay, so that is going to be our amplification factor. The A is amplification factor, and VL is the amplified signal. And this A can be designed depending on what the requirement is. Okay, so now from here, let's represent this. Again, we can say, what is this A, right? Or what is this amplified stage? What is included there? So the way we look at it is from the point of view of the source voltage, and also from the point of view of the load. Okay, so from the point of view of the source, okay, so that's my first point there, that from a point of view of source, you see a resistor, the load side, and that's what is being observed. And from the point of view of load, we observe a voltage source, right? So we see a So as I mentioned earlier, that the internal structure we're not too much concerned with at this point in this course, but in future you will see it. So I mean, we're not concerned with what type of transistor it is, what is the bias circuit around it within that amplifier, but we are going to be modeling it using the components that we are familiar with with in this course. So combining these two observations, one from the resistor side and the source side, and the one for the load side, we combine them together, right? So these black blocks could then be represented with this circuit here. Okay, so this is your source And the source is really observing is a resistor, okay? And from the load side, we said that it is observing a voltage source. So what does the voltage source include? The voltage source includes a resistor, and it includes some voltage, right? Some ideal source, right? So essentially, this value of this particular source is going to be factoring in this gain and the actual source voltage. So the value of this is going to be A V sub S, right? So now we can also observe that it is dependent on certain value, which is the gain, and this, the gain is sort of the factor, and the source voltage. So if you recall from a very early discussion, like in the earlier weeks of the course, we talked about the dependent sources, which are the four types. There's current source dependent current sources, voltage source dependent current sources. Then there's a current source dependent voltage source, and voltage source dependent current source, and then there is a voltage source dependent current source, and of course two other dependent sources, which are the voltage sources, and they are current source dependent voltage source and voltage source dependent voltage source. So this is a voltage source dependent voltage source, in which case we have a different symbol for representation of this. So let's go ahead and represent it using that symbol. And the symbol is simply this diamond shape. It still will have the plus and minus inside, right? So now we can say that we can model our circuit by this input resistance. Now we are looking at it, we're combining the two point of views together to model this. So there's an input resistance, and there's so basically two resistors, so we call this input and output, just based purely on the sides in which they are attached. So the input resistance, the output resistance, and the dependent voltage source. So this is how we model this amplifier in our circuit analysis. So by the way, this is the source resistor, and this is the voltage source. Okay, so next we want to have certain assumptions about our input resistance, output resistance, and the gain, right? So in terms of ideal behavior. But before we do that, we also observe that this is my input voltage, okay? And based on what we have here, we can then say that using current voltage divider, we can find this input voltage, okay? So the input voltage, again, this is a series circuit, and they're sort of separate loops. So we can say that the input voltage is the source voltage times the input resistor over equivalent resistance. Okay, so that's my input voltage. Similarly, we want the output side, so we have a voltage that is the output voltage that is seen on this resistor. So we can do the voltage divider on the output side also, which is again A V sub S times RL over RL plus R out. Okay. Now, ideally, what we want is this input voltage to be equal to Vs, right? So that's our ideal behavior. Again, I'll just mention ideal behavior here. And why I say it is ideally wanted, because we want the entire source voltage to be used as an input voltage so that we can observe the largest amount of gain, so that's in order for that to be true, we have to consider this. We have to design this circuit in such a way that Rin is as large as possible. So the largest resistor that we could see is, of course, open circuit, right? So if Rin is large enough to the level where we can say that Rs is negligible in terms of the magnitude. For example, if Rin is 1 mega ohm and Rs is, for example, 5 ohms. So a mega ohm versus 5 ohms is pretty much negligible. It's almost a rounding error. So in that case, basically, we can then cancel out this, because the Rs becomes a small quantity, and effectively what we have is Vn equal to Vs Rin over Rin, and then Rin cancels out, and therefore we have this relationship Vn is equal to Vs. But again, this is ideal behavior, not practical behavior. Okay, so this is an ideal behavior. In ideal behavior, we want this to be true. So that is on the input side. Now on the output side, we want the R out to be as small as possible, right? So if R out is negligible in terms of magnitude compared to RL, so we can say that R out so if we say that R out is equal to 0, essentially we can then, again, it's an ideal behavior, right? Because R out is 0 now, and then you can cancel this, and we can have VL is equal to A V sub S. So that's essentially similar to what this expression is, and that's the ideal behavior of this, right? So this is the effectively the largest possible gain without really considering all the resistances. Okay, so these are the two ideal case scenarios. So this is the behavior of an ideal op-amps. So these two observations are important. So we want the RS to be the Rin to be as large as possible and R out to be as small as possible. So in the end, the circuit that you end up with, it would look like this. So this is the ideal op-amp circuit, right? So you have a load resistor, output voltage, A V sub S, Vn, Rs, and V sub S. So you would have observed that we have taken out of the equation the output resistance and the input resistance and replaced the input resistance with an open circuit, and short circuit is replacing the output resistor. So this is the ideal behavior of a op-amp. Okay. As I mentioned, we are not too much concerned with what the internal working of this is, but we model this as a either a schematic symbol or a circuit symbol. Okay, so the schematic symbol, whenever you see schematics and you see an op-amp, you will see a symbol like this. Okay, so there are two ports here on the input side and one port on the output side. Okay, so this one is non-inverting input. And the negative side is the inverting input. So, and this is the output side. There are other ports which are typically not shown on the schematic, are the where you will connect the voltage source that is providing voltage to this device, right? So this is separate from the input and output voltages, but in order to energize this device, you would need certain voltages. For example, if you have a 10-volt voltage source, then this will be the plus 10 and minus 10 of the voltage source will be connected there. Okay, so these are the terminals of the power supply that need to be connected there. Okay, so this is how the circuit would be observed. Now, where do you connect your resistors would matter a lot. Now, if you connect the active resistors, or the circuit is connected to the inverting side of your device, then essentially what you want is you want the voltage to be basically the output voltage to be at a phase difference of 180 degrees, right? So essentially, if you have a plus 5 volt on the input side and the gain of 5, for example, and you're connecting everything to the inverting side, then basically 5 times 5 is 25, but again, the output is going to be a negative value. So it's going to be minus 25. So it will basically it will basically amplify the signal, but it will be at a phase difference of 180 degrees. So it's going to be opposite polarity. Okay. So that's one thing to consider. The non-inverting side is when you don't want the voltage to change polarity. So essentially the output voltage would be at the same level. So I mean, this not going to be a negative sign with it when you're doing the calculation. Okay, so that's the main difference there. Now, in terms of the circuit schematic, circuit symbol or representation there, I mean, it is basically internally, it's connected like this. You have the input resistance, and then you have the dependent voltage source connected to ground. And this is your output. And the input, for example, if this is a positive and negative, would be VP and VN. And of course, you have the local voltages also. So this is your R out. So I mean, this is how you would, and it's the same thing as, we have seen here, in this circuit. So we're replacing it like that. Of course, you would not show it with this amplifier symbol. What you would just simply show is replace this amplifier and and define your circuit, and then do the analysis just like you've been doing it using the techniques from the previous chapters and weeks of learning. So all those techniques, nodal analysis, mesh analysis, all that need to be applied in order for us to calculate the desired quantities. Okay, so so here is the summary of ideal op-amp characteristics that we would, I'll just write here. Okay, as we said, we want the input resistance to be very large. We want the output resistance to be very small. And we want the gain to be as large as possible, right? So ideally, it should approach infinite gain, right? Of course, in reality, it's not going to be that, but ideally, we want that, okay? So let's first look at a negative feedback connected circuit. So it's basically an op-amp circuit with negative feedback. So the circuit is showing a source voltage, source resistor, let's just connect it to ground like that. This is my RS. And since it's inverting terminal is connected, so we sort of flip it, but rest is pretty much the same. So the positive terminal is then connected to the ground. And on the output side, you can connect anything here, like some kind of load, but again, we'll just represent it by the V sub O here, the output voltage. And we need to have a feedback path here, which is part of our, let's just call it R sub F, representing the feedback resistor. So it is a inverting device. So it's a negative feedback. So it's a op-amp circuit with negative feedback. Okay, so that's how you represent it, right? Now, again, this is a circuit schematic symbol, but we want to now simplify this more, and we translate this to this form. And as we said, the ideal behavior is this. This is my V sub N, this is my V sub P. The input voltage is this, because we want the Rn to be infinite, right? And then on the output side, this is also connected to ground. And I want the output resistor to be as small as possible, so it's a short circuit essentially. And then you have your here I can just simply represent it by AVN. This is my V sub S. Okay, so this is how we translate this symbol into a circuit. So now we have effectively created a circuit here, which is in a form where we can now solve it, right? So the gain effectively is something we call the factor by which the output has been improved with a given input, right? If you recall that expression, we said that VL was representing the output, and there's a gain and V sub S. So from this, if I were to derive the gain, essentially it is in this form, by the way. So V output is A times Vs. Previously, we were just representing it by the V sub L, but now since we don't have a load here, we're just simply showing it with the V sub O. Symbol changes, but the quantities are exactly identical. So now if I were to derive A from there, the amount of gain, I would divide both hand sides by V sub S. So if I did that, I will then essentially get to this form like that. Okay, so initially you have VO is equal to A times Vs, and then we got this form from there. Okay, so what I'm looking for is the gain here, right? And I will have to find that in terms of the resistor values. Okay, so let's go through this analysis. The first thing we want here is the value of so I want to get some, let's say this is my currents, this is, let's say I1 and I2. So I want to now write an expression. Let's say this node is called, let's just call it node number 1. Okay, so let's write the equation at node number 1. So the current entering there is equal to the current leaving there, because that's only two currents that are coming in and out of this node. Because if you look at the next component that is connected there, that is the infinite resistor. So of course, there's no current that can pass through a large resistor. So it's effectively open circuit. So that's the only path for the current to proceed from there. So then we can say is, I1 will have to be equal to I2. Now, what is I1? I1 is Vn. It can be written in terms of the Vn. So we can say that it is Vs minus Vn over R sub S. And we have here Vn minus V sub O over RF. Okay, so that's what I have from here. Now I need to simplify this further. Just give me a moment. My cursor has disappeared. Let me get it back. Okay, so if I do cross multiplication of this equation, So what I'll end up with is RF times V sub S minus Vn equal to R sub S Vn minus V out. Okay. Simplifying it further, we are going to get Vs RF minus Vn RF Vn RS minus V out RS. So if you combine the like terms, we can then rewrite this equation in this way. Okay, so we'll leave it at this point, and let's just call it equation number 1. Okay. Next, what we want is now we want to write on the output side, right? So the output side, if I look at the output voltage, I have the simplest way, I mean, I have different ways of analyzing it. I can do nodal analysis, I could do mesh analysis, I could do voltage division, current division. All those techniques are available to me. But if I look at it, it's a pretty straightforward equation. So if I look at this in terms of the mesh analysis, I can write the equation for output voltage. So the output voltage is pretty straightforward here. We can say that V sub O is equal to, or let's just write it like this. That's the value of your source voltage, because we're seeing the negative terminal first, so we'll write it like that. And the positive terminal of V out, that is all equal to 0. In other words, we can then say V in is AVN is equal to V out. So I just took it to the other side and then switched the values. Effectively, that's the same thing. Now, next thing I want to do is I want to write this in terms of the input voltage. So we can say that V in is equal to V out over A. So I divided both hand sides by A to get to this equation, right? Now, when I did that, also my third observation for the for ideal op amp is that I need to have infinite amount of gain. That's the ideal behavior. So if I apply that constraint here, then I can say that anything divided by infinity is 0. So Vn is equal to 0 then, right? So if Vn is equal to 0, by the way, this is separate analysis. So if Vn is equal to 0, then Vn can also be written in terms of the difference in voltages, which is the Vp minus Vn. That is your, essentially the difference in terms of the both sides of that resistor are the P and N terminal. So that what we can say. So if Vn is 0, we can have this other observation, which is VP is equal to VN, right? So that is going to be your other observation. But if you look at the circuit more carefully, what is VP connected to? Okay, so VP is connected to this ground, and ground it is at 0 volts, right? So VP is connected to ground. So what we can then say that and if VP is equal to 0, then Vn is also equal to 0. Okay, so that's my it's a very important constraint in terms of ideal op-amp analysis. But as far as so there are two things you can observe from there, but the key point here is that you know your V in is equal to 0, but as a side note to that, you know, as Vn is equal to Vp minus Vn, therefore, you know, Vp minus Vn is equal to 0 since V input is 0. So therefore, then the two are equal, and then since Vp is connected to ground, therefore Vp is 0, and hence Vn is also 0. Okay, so now if we take this information and apply it to this equation number 1, where we are saying that Vn, the letter N, is 0, then this term would be 0 then, right? Because you're multiplying Vn to Rf plus Rs. So therefore, you would get zero minus okay. So that's your reason for why we turn this to 0. So now we can write this as Vs Rf is equal to minus V out Rs. Okay. As I mentioned earlier, the gain, or let's write it like this. Is equal to output over input, just to make sense out of it, right? So the gain is represented by A, the output is represented by VO, and the input is represented by Vs. So we want to bring, let's just call it equation number 2. We want to bring equation number 2 to this form, okay? Okay, if we do that, then what we will get is, so let's write equation number 2 here, which is Vs Rf is equal to minus Vo Rs. And again, the goal is to bring it to V out over Vs. So if we divide both hand sides by Vs, okay, we can partially get there, right? So then what we will have is Vs Rf over Vs is equal to minus V out Rs over Vs. Okay, so Vs and Vs cancels out here. In other words, what we get is is essentially we can shift sides also. So we can say that minus V out Vs R sub F is equal, sorry, now if I divide both hand sides by R sub S, so I divide both hand side by RS. This gets cancelled, and what I get is minus V out over Vs is equal to Rf over Rs, right? So in other words, we can then bring it to the desired form. If we multiply both hand sides by -1, we are going to get V out over Vs minus Rf or Rs. Okay, so that is your gain essentially. So if we observe, okay, so this is my gain for this circuit. If I were to analyze this circuit, and I'll give you an example also shortly, but right, you notice that this is the format by which we are connecting it. Is a feedback resistor, and there is some resistive network. Which is connected to the, again, it's not going to be a very straightforward problem where we'll have some resistive network representing R sub S. So this is going to be R sub S, and there may be some resistor network in the feedback side also. It's just a single resistor here, but you could have certain linear circuit on the top. So you have to resolve this and bring it to the simple form, which is this. Okay, so the simple form is this. Okay, so once you bring the circuit to this form, then you can apply this equation or this formula and find the gain for it, right? So this is the essentially the closed loop gain. The open loop gain is essentially the infinite gain that we want for ideal amplifiers. But in this case, we're running it in a scenario where we are connecting resistors to it. So therefore, you have this R sub F, which is the feedback resistor, and that is going to define what the gain is. And based on this formula, if you see the feedback resistor connected to the negative terminal of the op amp, then you can use this formula and find the gain of it. Okay, so let's look at an example here. Let's look at this example. We have a source voltage connected to some resistive network. Voltage level here, and so, and in between I have a op amp connected here, negative terminal, positive terminal. Okay, so there's some resistor RL here, and then we can say that this is my output voltage. Okay. This is V sub S. This is 10 kilo ohms resistor. This is a 15 kilo ohm resistor. There's also 15 kilo ohm resistor. And this is 150 kilo ohm resistor. Okay, so we're not concerned with what RL value is. So now here, I'm asked that what is the gain, right? So what is the gain of this circuit, right? So here we can, since we have observed that the feedback resistor is connected to the negative terminal of the battery or the negative terminal of the op amp, therefore it is a inverting amplified circuit, right? So if it is inverting amplified circuit, then my gain can be represented as minus RF over RS, right? So RF I know is is 150 kilo ohms, right? But what is RS? RS is not in a standard form here, right? So what we want to do is we want to bring this to the Thevenin equivalent circuit, which shows a voltage source connected to a resistor in series, and that resistor is your source resistor. So once you find the value of that resistor, you should be able to find the gain here, right? So let's go ahead and work with this circuit and then sort of isolate it at this point, because that's what our input side is, or you know, the source side is. So we're concerned with the source at this point. So my circuit will then look like this. So now this is your standard two-port network, you know, what we're familiar with. So this is my two-port, and the output, we can call this as V sub O. Let's just change it to something let's just call it V sub O1, for example, just to distinguish it from the output voltage that we're using. So here we have these three resistors. Now there are different ways we can approach this. The goal is to bring this circuit to this form. That's what the objective is, right? Now, using, you know, you can use the, how you can find R Thevenin. You know, so finding R Thevenin, one way to do it is by shorting voltage sources and open circuit current sources. So if I go through that technique, then essentially what I will have, so that's one technique. The second technique is to apply the source transformation, but for source transformation, I need to know what the value of the voltage source is. Since I don't have the value there, it's just represented as V sub S. So therefore, what I will do is I will use the Thevenin resistance calculation technique. So I will convert this to this form. So again, this is 15 kilo, this is 15 kilo, and this is 10 kilo. Now, if you look at the 10 and 15 kilo ohm resistors, they are in parallel. So we can then represent this. Let's just call it R equivalent 1, which is the 10 kilo ohm resistor in parallel with 15 kilo ohm resistor. And this one is again in series with the 15 kilo ohm resistor, right? So okay, so again, you can use the technique you're comfortable with. I'll just do this 30K, so I'll find a common, so that the 10 and 15 are the common factors to a number. So I selected that number, which is 30. So 30 is a value that both of these are factors to. So this is by a factor of 3, and this is by a factor of 2, right? So essentially what I will have is 1 over R equivalent is equal to 5 divided by 30K, right? And if I do that and I do cross multiplication, so I have 5 times R equivalent is equal to 30 kilo. Again, I can assign the ohms here also, and divide both end sides by 5. I'm going to get 30 kilo ohm divided by 5, which is going to give me 6 kilo ohm, right? So my resistor R equivalent 1 is equal to 6 kilo ohm. So essentially what I can then say is this is a 15 kilo ohm here, 6 kilo ohm here, and they are connected in series. So bringing back my voltage source now, the series combination of these two is equal to 21 kilo ohm. Okay. So now I brought this circuit to this form. Looking back at this, I'll just write it here. So this resistive network can be represented by this 21 kilo ohm resistance, and okay. And this is V sub S, right? So now it is my standard form. The RF is 150 kilo ohm. So I brought this circuit to a standard form, and RS is now 21 kilo ohm. So I can now calculate my gain, which is minus 150 kilo ohm, whether this is 21. And if you do this calculation, you're going to get minus 7.14. So typically gain doesn't have a unit here because it's a factor by which you multiply the input in order to get the output, right? So my gain is 7.14 negative value. So which means that we shift the number, shift the voltage in terms of the phase, and we are increasing it by a factor of 7.14. So if it's a 2-volt input source, it's going to become 14.28 volts, but in a negative value, right? So as I mentioned, the theory is a little bit detailed, but as far as application of this is concerned, you simply have to use these formulas and bring these circuits to a little bit more standard form and do the analysis and apply it there, right? So these techniques, all this is from previous knowledge, so that's not going to be hopefully not as challenging, but recognizing where you need to start from. So the value you want to start. So again, the node at which you see the feedback resistor and where the op-amp is connected is where you would start your analysis from, and then you simplify one side or the other side and essentially get the circuit to a standard form. So I just wanted to show you this derivation that I did earlier on in order to get this so that you understand where these formulas are coming from. There are 4 types of op-amp circuits that are listed in your book. You can see that. We'll talk briefly about the other ones also, and maybe solve some examples also. So I won't go through the derivation of the other ones, but if you're interested, because just in the interest of time, we don't have a lot of time left in the term, but the derivations are listed in the textbook if you're interested, and if you can review them, and if there are any questions, we can have a discussion about it in our future lectures. But what I will do is I will use those formulas to solve a few problems in the next lecture that we have available on Thursday. So just to summarize, the formulas are important to us, right? So you want to keep those, know how we got there, but using it is just a simple formula and simplifying the circuit to a more reasonable or to a form where we can apply that formula. Okay, so that's what I'm trying to say. All right. So are there any questions about any of this analysis or anything that stuck out for you that you want to clarify?
No, I don't know where to. It's a lot.
Yeah. As I mentioned, this part of the analysis, I won't be really testing you on any of this derivation part. The important thing is to be able to see a circuit, let's say in this form, and then convert it to a more standard form, which is this. And I think if you hopefully if you review the notes and then because right now we are taking notes and I'm also describing the concept. So once you review the notes, you may have some questions, and also sort of reinforce some of these concepts in the next lecture. So I won't be covering any newer material. I mean, we will be looking at different types of problems, but again, it's going to be pretty much, I won't be doing any new derivations, what I'm trying to say. So let's just conclude the session here, since you don't have any questions and you probably need some time to sort of observe all this material, and then we'll convene back on Thursday and take it from here. Okay.
Okay, sounds good.
All right, thank you.